We've been discussing the Fundamental Theorem of Calculus, which states if you have some continuous function f, at least continuous on an interval, then the definite integral of f from a to b, that is the area between the graph and the x-axis, is given by the antiderivative of f, big F, at b minus the antiderivative at a. So you can find the area just by finding the antiderivative and plugging in. Now, I've been calling this the Fundamental Theorem of Calculus, but often it's referred to as the second part of the Fundamental Theorem of Calculus. I find it's easier to introduce this first, but it's often presented as the second half. What is the first half of the Fundamental Theorem? Well, it's going to say the same thing, but kind of opposite. Instead of saying that the definite integral is the antiderivative, or the difference between the antiderivative, it's going to say that the derivative of the definite integral is the original function. But now we have to be a little bit careful to make this make sense. If I just put here the definite integral from a to b, if this was just from a to b of f of x, then it would just be some number, right? That comes out to be a number, the derivative would be 0. So instead, in order to make sure this is a function of x, I need to make this the definite integral from a to x, the variable x. And then here I'm going to use a different variable t. So let me show you what I'm trying to do here. So here, imagine I have some graph, and I want to talk about the area from a to x, where x is a variable that's changing. So you might think, here's my graph. Up here's my graph of y equals f of x. And maybe 1 minute you want to know what is the area from, say, a equals 1 up to a equals 2. And then you want to know what is the area from a equals 1 up to a equals 3 or 4 or 2.1. So you want x to be able to slide around, to change from one height to another height. So x is a variable. This expression here, area from a equals x of f of t dt, so imagining this now as the t-axis, is going to give me a function. This is going to be a function of x. This is going to be a function of x, where it's going to tell me, well, if x is, maybe it's 2, that's where my area is, or kick out whatever the area is. If x moves up to 3, it'll kick out whatever the area is. But it's a function, and this value changes as x slides from smaller to larger values. So now this whole thing is a function of x. And so what is d dx? D dx of this is asking me, how is this changing? So you can think of d dx, you can think of this as asking, what is the rate of change, because rate of change, that's what my d dx is calculating. What is the rate of change of the area, of this area, as x changes? As x changes. So it's just asking, as x moves over to the right, or as x moves over to the left, but as you think about x changing, x increasing, so as you increase x, as x grows, how much is this going to grow by? And when doing derivatives, you're thinking about infinitesimal changes. So if you slide this over infinitesimally small, how much does the area grow by? And the answer of the fundamental theorem is question, how much is x changing by? Answer, it's changing by the height of your function. F of x is the height of this function. This is f of x. If you're at x, f of x is your height. And so you can think the area is changing by adding another slice here. This slice represents your f of x, it's your height is f of x, and so as you change the area, it's by you're adding little infinitely thin rectangles onto it. Okay, that might all seem quite abstract, but let me show you concretely what's going on here. So let's do a couple examples. So you ready? Let's do an example. Let's do an example of what would be the derivative of, let's say, the definite integral from 1 to x of cosine of t dt. Now, what you could do, one way you could solve this, is you could begin by first calculating this definite integral. And you calculate this definite integral, how? Well, simply by coming here and saying, okay, the definite integral from a to b is the antiderivative. My antiderivative of cosine will be sine. So that's sine of the top value x minus the bottom value, which is 1, so minus sine of 1. So I found my antiderivative. So the antiderivative of this just came out to be sine of x. And I plugged in sine of x, well, sine of t, I guess. So this was originally in t's, so the variable was t. But now I plugged in an x for the top and a 1 on the bottom. Okay, that's this piece. Now I still need to find my derivative. I still have this d dx up front. So now we come and we do d dx of that. And we say, okay, d dx of sine of x is cosine of x minus d dx of sine of 1. Well, sine of 1, this is just a number. I don't know what the number is. It's, type it into your calculator. It's not a nice number, but it's a constant. It is just a number. It's not a function. Or the function is constant. It's not changing. So the derivative of that constant is 0. You're going to take the derivative of that. That just goes to 0. And so you can ignore that, minus 0. And you're left with just cosine of x, which recognize that's just your original function with just the x plugged in. Okay. That's what this is saying. Although here, we actually found the antiderivative. If we know, though, we're going to find the derivative in the next step, we don't have to go through this process of first finding the antiderivative and then finding the derivative, because that's just going to cancel. Like think about if you had maybe a more complicated problem. Like, what is the derivative of something like, oh, I don't know, let's say the definite integral from, it doesn't have to be 1, it can be any constant. So let's say -3 up through x of t squared minus 1 all over t cubed plus 3 dt. Okay. Maybe you can figure out what the antiderivative of that is. I don't know what it is, like we could work it out, we could try and see if we can figure it out, but it's not obvious to me. Okay, well, I can think of a few tricks, but like it's not obvious how you would find that antiderivative. But you don't have to know what that antiderivative is, right? You can just say, I don't know what the antiderivative is. I'm just going to call that antiderivative some big F. I don't know what it is. But I know from the fundamental theorem, I would find the antiderivative of this guy, to find this definite integral, I would find the antiderivative, whatever big F is, I would plug in x minus the antiderivative, plug in -3. But now, since we're being asked to find the derivative of the whole thing, since we're being asked to find the derivative, we're going to find the derivative of the antiderivative. That's just going to take you back to whatever your original function is. It's just your original function of x minus the derivative of big F of -3. Well, whatever this function is, when you plug -3 into it, it's just a number. So again, just like before, this piece here is just a constant. This is just a constant, So when you take the derivative, it goes to 0. So you're left with just little f of x, which means you're just plugging x into your original function. It just comes out to be x squared minus 1 over x cubed plus 3. So that's what this is telling you. If you're ever asked to find the derivative of the definite integral from a to x of some function of t, just plug x into the original function. You can kind of think loosely that what's happening is the derivative and the antiderivative are canceling out with each other. They're canceling out. You just have to keep track of the variable change. Now the x is being plugged in. They're just canceling out with each other. Okay, so 2 statements of the fundamental theorem of calculus. I like to use the second one to think about the first one. You can also use the first one to think about the second one. They're related to each other, but both are trying to say that definite integral is just finding the antiderivative. So finding the derivative of the definite integral is just taking you back to the original function. Derivatives and integrals, and definite integrals, they're the opposite of each other. They cancel each other out in some sense.